Hello everyone and welcome back. In this video we're going to move on to take a look at smoothing as we have little jaggies all over the place and it would be nice to get those smoothed out. Lee.
Right. All right. For smoothing, how are we going to do it? Jason, what are we going to do?
I don't know, we're just going to smooth it out with a magical equation full of penguins.
Sweet. Penguins. I never thought about penguins.
That's the best way to go.
I figured elephants would probably be a better job. They just drop them on the pointies and
Well, we're
they
going to do a
flatten them.
whole bunch of averaging, huh?
Yeah, what we're going to do is we're going to look at our grid, and if you look at our grid that we did way back in the first R&D set, we did this nice little I think these are what, pentagons, I believe they're called now. Or,
Pentagons? That's
well, hold
five.
on. One, two, three, four, five, six hexagons.
Hexagon. Very good.
Yeah. There we go.
And
Hexagons. Well, geez, it's only 3 in the morning.
and you'll find that there are 6 different vertices that we can sample if we take any center point. We should have 6 surrounding it.
Right. And what smoothing is going to do is sample each one of these 6 points. Hopefully, you can see my mouse moving around.
Yes, they can.
Okay. And
Actually, let me do this. Yeah, there you go. Very good.
yep. All right. So each one of these 6 points surround every center vertex. So what we're going to do is we're going to sample all 6 of those, average them together, and then compare the difference between the heights of that average and the center vertex. And then in the case that we're going to do for this implementation, we're going to reduce this altitude or average the two by 80%. So if this is, let's say, 1 unit above or 1 meter above the average of everything else, after one iteration of the smooth, it will be only zero point 0.8 above it. And then it will continue to do that for the number of iterations that we define.
Okay.
So it is it's kind of a exponential function in the fact that you will never ever reach the point where this vertex is exactly equal to the averaging because you're only taking 20% of it each time
Hmm.
away. So let's go ahead and start coding that up.
All right, let's see. You might need me to help you
This
jump back over there. And here you go.
it's kind of like I need somebody to hold my hand, which because I just can't do it on my own. All right, we need another method to pull this off. This will be a public method because we need to have it exposed externally. It's going to return a float, and we're going to call this get smooth height. Once again, my really awesome naming conventions to the rescue. We're going to take in a float x, a float z, or z, and we're going to take in an integer, which is going to be our iterations. From that, we're going to specify a height, and after everything's done, we're going to return that height. All right, good. Smoothing's done. Don't think it's
We're
going to
going to
work.
return the height with another var of height. That's illegal. Type the word return instead of var at the beginning of line 24. Thank you.
No. I like 2 bars. I had typed it. It was the computer's fault.
Okay, good enough.
All right. So, all right, we're done. We're smoothing everything to 0.
Yeah, we are, that's for sure. But you're not actually calling get smooth height, so we're not doing anything, to be honest with you.
Yeah, that's true. Okay, let's call get smooth height then. Let's copy this. Now, where do we need to call it from? Inside of terrain patch. So everywhere we're calling get height, we're going to call get smooth height. And these are going to give me errors because I'm not specifying the number of iterations yet. To specify the number of iterations, we'll come up here and set another constant. So private const int, and we'll call this one smoothing iterations. And we'll set this to, let's say, 5 for now. Take that. And scroll down to everywhere that we just broke. And add smoothing iterations to it. Okay, now we're calling it all and everything's being smoothed to zero.
Much better. Yep.
Again, while it functional, probably not the most ideal results that we want to go for.
No.
So what do we need to do? Well, we know that the smooth, we need to be able to get our height. To get our height, we'll just end up having to call here. So let's go ahead and do that. So we're going to say get height, and we're going to pass in X and Z or Z. So now we're essentially just doing what we were doing all along, but we're just doing it via another method. Now there's a couple of things that we're going to need to know. We need to know spacing. So we're going to get our spacing. We'll call spacing, just because it makes the math work a little bit easier, we're going to call it FS for spacing. Don't ask me how I came up with that.
I'm not.
Now for spacing, we need to reference our terrain patches spacing. And right now it's a private, so we can't get access to it. So let's turn that to public. Yeah, probably not the most ideal, but it functions and it works. So we'll say get terrain patch spacing. Now we need the half space. Oh, that's where FS came from, full spacing. HS is half spacing. See, I knew there was a reason to it. Just couldn't remember what it was. This is why you should comment your code always. All right, now the reason we need full and half spacing. We don't need so much the, well, yeah, we will need it. Let's get back into Photoshop. The reason we need it is we know where any vertex is, which is in this center spot. But we need to be able to calculate where these other positions are. So a full space is going to be one whole vertex this way or one whole vertex this way. That's a full space. Now, if you look at the ones above and below our selected vertex, and hopefully you guys can see my mouse, these are half spaces. So whatever this x is, this is a half an x less than, or half space less than that x, and this one is a half space greater than this x. That's where the half space comes in. So get back to code. Now we're going to need some other height. We're going to need the upper left height, and to get that we're going to use get height. And we know x, and we know upper left is going to be a minus half space from x, and it's going to be z plus a full space. So once again, if I jump back into Photoshop for that to explain it, we're looking for the upper left point here. We know it is a half space from our current x, so we take x minus a half space, and we know it's z or z plus a full space high. So that's how we're calculating, and we're going to use variations of that premise to get each one of the surrounding vertices. And I did it again.
Wrong alt tab.
Wrong alt tab. Which is like, get me back. Right, so that's the upper left. We need to do the same thing for upper right, our left, our right, our lower left, and our lower right. So upper right, left, right, lower left, and lower right. So upper right is going to be a plus a half space. Left is going to be minus a full space, but no modification to z. Right is going to be plus a full space, and also no modification to z. and then lower left is going to be a minus a half space, and minus a full space for Z, and lower left again minus a full space for Z, and it's going to be plus a half space. Okay, so that gives us our 6 samples around the outside of our current vertex. Now we need to get our average height. So we're going to get a new var, average height, that's going to equal the sum of upper left plus upper right plus, whoa, let's try that again. Upper left plus upper right plus left plus right plus lower left plus lower right. And because we're summing 6 numbers and I want the average, we need to divide by 6. See, there's no real hard math in here. It's just lots of little simple math that adds up to a real complex solution. So now we're averaging all of our heights. We've got our original vertex height and the surrounding average heights. We need to be able to step through this and iteratively knock down the height of our center vertex. To do that, we're going to do a for loop instead of a var. So, forgot. Nelson's version of the IDE doesn't do that for you. Or he's probably, actually it probably does. He has it bound to a hotkey, is my guess. And I don't know that hotkey. But we want to have a for loop that loops through the number of iterations. And each time through that loop, we want to take our height, and it will be equal to, well, let's do it the other way instead of that way. Let's do the mathf approach and use a lerp. And we'll say that it's going to be the lerp of our height and our average height by 0.8. So actually 0.2, 20%. It's 0.8 if I was doing it the other way, but this way we want to maintain 20% of our original height each time while lerping towards our average height. So each time through, we're only knocking off 20% of the height. Now, one of the things that we need to compensate for here is the fact that we're using an exponential curve to define our altitude. So our heights, as you approach either 0 or 1, are increasing exponentially to our max height, either in the positive or negative, depending on if you're above or below 0.5. What this means is as you approach those extremes, our vertices are going to have more and more of a stretch or a larger distance, which means at those ranges, in the mountain ranges or the deep valleys of the ocean or trenches of the ocean, we're going to have much more occurrences of those little spiky triangles, and we want to knock that down. To do it, I'm going to implement something I'm calling adaptive iterations. Basically, I'm going to take a look at how much above that the vertex is above its surrounding heights, and if it's a very large distance, I'm going to add even more iterations of smoothing to just those pixels. So we get less iterations on the low-lying vertices in the rolling hills. That keeps some detail there and not completely smooths them out. But in the mountains and the trenches, I want more smoothing so we don't have a lot of little spiky spires all over the place. So let's go ahead and do that. So we're going to make another var. We'll call this adaptive iterations. And to figure out how many adaptive iterations, what I'm going to do is take the integer of our height minus our average height. So I'm looking to see how far above or below our average height is, our height is above our average height. And I also need to make sure that I take mathf dot absolute, because it is possible that we have a vertex that is less than our average height. And if it's underneath the ocean or even in the mountains, it is possible we've got one vertex because of noise is substantially lower than all the others. So we want to make sure that we do the absolute difference between height and average height and add an appropriate number of adaptive iterations. But I also want to cap that. I don't want this thing to go crazy and go, oh, okay, well, this one vertex is 50 meters above the other one, so I'm going to iterate through 50 additional times. That will slow us down too much, so I'm going to put a cap on it. To do that, it's just another condition that says if adaptive iterations is greater than 5, then adaptive iterations is going to equal 5. So this will, in effect, add up to 5 additional iterations of smoothing depending on the differential in heights. This, again, is an R&D type case, and this is what has worked well for testing. In a final product, this is probably going to be a set of variables that you'll want to set up that can be changed without having to come in here and mess around with the code, both the adaptive iteration max count and also probably the smoothing amount would probably want to be exposed at some point so they can be changed. So if we build this out, make sure we have no errors if we want to run that and see what we get. And depending on the number of smoothing operations you're doing, you will notice that it does take longer to load in the map. Not incredibly longer because we're using a low number of iterations with a max of 10, but we do start to see the smoothing. And you start to see the power of the noise with the smoothing. We, in effect, get what looks like erosion along the ridges of the mountains. So you can see where it looks like material is starting to slide down. And we get a very convincing looking terrain, but we have no erosion. We're not calculating this with noise. We're just using 2 different texture maps to build all of this in real time. And if you wanted to get creative with it, you could take our base map and use that as a single channel in our texture, and that would still free up 3 more channels in that same texture that you could use for different types of noise. So you could mix and match noise and get creative. In the end, in a final product, we could very well set this entire base terrain generation process to use a single texture, but still maintain the ability to have a base map and noise maps. But it was easier in this set of videos to just demonstrate it with 2 different textures.
Okay.
So
did you want to just demonstrate some different iterations, or?
Yeah, we could do that. We could knock up the number of iterations if you want to pause it. Let's go ahead and go into terrain patch, and let's bump that up to 25.
All right.
Now this will take even longer to calculate. So the more iterations you've got, the longer it takes. But it definitely starts to round stuff out.
Cool.
But you also have to remember that there's going to be a trade-off. The number of iterations will only get you so far because we're taking 20% away of the height each time. So there will be a point where you just won't be able to take any more away between the difference between vertices, because we're only sampling a vertex with its surrounding. So if I bring up Photoshop again, no matter how many iterations you go through, there's only so much that you're going to be able to knock down one vertex with its surrounding vertices.
Right.
Now, if you wanted even broader range, you would have to modify the smoothing algorithm to take into consideration larger amounts of area. If you wanted to say, if we go back, I believe you still left it running.
Mm-hmm.
If this ridge was too sharp and you didn't want it there, this type of smoothing is not going to get rid of it because we're only sampling one vertex distance around any given vertex. So for something like this, you need to look at our sculpting tools that we're going to be playing with to have a wide scale smooth that would smooth everything all at a go.
Right. All right, very cool. Well, Lee, does that pretty much wrap it up for this video?
For this one, yes.
All right, well, thank you guys very much.